we do have, our class does today go till 11:30 instead of 11:25. So I want to kind of wrap this up here. I know I haven't seen you since Thursday, so let's see if you remember some of this stuff up here. First of all, if you're drawing these, and part of the the first part of the test is where you actually draw these little arrows. These arrows are called dipole moments, and it simply has to do with electronegativities. Everybody, I know this is Monday, and I haven't said that word for a while. Electronegativity. When atoms are sharing electrons, which one tends to pull the electrons toward it more than the other? That's called electronegativity. And so let's take this one right here. Here. This is an easy one. The one first one they started out with was hydrogen fluoride. And we find out, you look on there, and this electronegativity is 2.1, 4.0. That's a pretty big difference. That's almost, 1.9. And 1.9 is clearly not purely covalent. It's not quite in the ionic zone, not quite there, but it's going to be a polar covalent bond. Now, because there's only one, and when you draw the arrows, everybody see how I draw the arrows again? Which way do you draw them? Right, the arrow goes toward their electrons. They're going to be spending more time. That's called electron density. And then that's going to leave this end slightly positively charged, okay? It's not a full positive charge, otherwise it'd be an ion, wouldn't it?
Thank you.
Okay, sure.
Appreciate your help.
Okay, you're welcome. Okay, so here's a neat little false color imaging. If they can measure the density of electrons, the red would be the more dense, and this would be an absence of it. Now, that was pretty simple because there's only one bond, that's one dipole moment, so would there be a net dipole moment? Yeah, there's nothing to cancel that out, was there? So now let's go down here with water. Let's go to water. Dipole moment here, 2.1, 3.5. Another one here. What's the net dipole moment? Would there be a net dipole moment? And which direction would it be? See that? So the oxygen end would tend to have extra electrons and be slightly negatively charged. Is that correct? And the hydrogen end would be partially positively charged. That's called a polar molecule. Look about ammonia, NH3. If ammonia had been flat like this, then everything would have canceled out. But it's actually up, isn't it? Up a little bit. I don't want to get too fancy today, but does anybody happen to know why didn't these go ahead and just straighten out? What prevents these from just saying, whoa, I'm getting away from you. I'm going to get away from you. And what makes water not linear? You might have an idea about that. It's kind of interesting. That's Monday, isn't it? That's a hard question on Monday. Anybody know how many valence electrons a carbon have? Look up on the periodic table. 4. How many are involved in bonding here? See, one of yours and one of mine. One of yours, one of mine. Only 2 of the 4 valence electrons are involved in bonding. So guess where the other 2 are? Right here. So the other 2 electrons sitting there act kind of like a third leg, don't they? So here's electrons, and they try to spread out. And that makes this molecule kind of bent here. Same thing here. Nitrogen has, how many valence electrons does nitrogen have? What column is it in? 5. Okay, and so 3 of them are involved in bonding here, and it means that there's a pair of electrons right here, and that's also kind of makes that 4th leg there. All right, what about carbon dioxide? Why is it not polar? It's got this polar covalent bond. It's got this polar covalent bond. It even has 2 of them. These are double bonds, aren't they? So you got 2 arrows going that way, 2 arrows going that way. But is there a net dipole moment? No, they cancel out, and that's why you would say it's non-polar. All right, last thing, then we're going to move on. And by the way, what I'm asking you to test are kind of the same ones that I have here. Got that? I'm not going to. You don't have to color them. I'll have you draw arrows. I'll ask you to draw the arrows for each bond, and then I'll ask you to draw another arrow for the net dipole moment. And if there is no net, you just say no net dipole moment. All right, so let's take a look. What if you're linear? If you're linear, what do you think? What do you predict here? Whether they're going this way or this way, they're going to cancel each other out, aren't they? Either two of them going that way or two of them going, they're going to cancel each other out. I'd expect this to be non-polar. What if you were planar, but there were three things there? Planar means flat. What would you expect there? What do you think? I would say non-polar because whether the arrows go in or out, they're going to all cancel out to a no net dipole moment. And then this one is a shape you're going to run across, especially when we do organic chemistry. Very special shape in chemistry called a tetrahedron. Does everybody know what that is? It looks like a pyramid, but the pyramids in Egypt have square bases. That's why they're called pyramids. But a tetrahedron, even the base is a triangle. Every side is a triangle. Get that? That's the difference between a tetrahedron and a pyramid. Tetrahedron would have something like, here's carbon. See carbon right there in the middle? And here's hydrogen, 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 hydrogen. This is methane gas. What would you predict there? Polar or non-polar? And what do you think? Whether or not the arrows are going in or out, what if all four of them went out? What would be the net? Would there be a net? No. What if they all went in? No. And so the tetrahedron shape is also non-polar thing. Did you guys talk about tetrahedron in your biology class at all? Okay. All right. Anyway, then they do some other ones. HCl. They do HCl. And I think they do, two more? And what is this one here? Oh, here's hydrogen sulfide. Okay, hydrogen sulfide. You look up electronegativities. Let's do that real quickly since we haven't done that. What's hydrogen is, let's see, hydrogen is 2.1, right? So 2.1. What is sulfur? 1.5? Oh, 2.5. Okay, it should be up there. So the difference would be 0.4, right on the edge, wouldn't it? Right on the edge of being a polar covalent, right? Like right on the edge. So it's kind of just a little bit of polarity. So we would draw it toward here, right? And we would draw it toward here. And would there be a net dipole moment? And that's what they drew right here. That's kind of neat. That's something you definitely, I would not teach that in the 10th grade. That's very much advanced. Even though you have polar bonds, it doesn't mean they're going to be a polar molecule, does it? Okay, what do you think? You okay on that? All right, a little bit advanced stuff right there. All right, now we're going to go back and let's do the last part of the of this material. Tell me from 10th grade or this year, what kind of reactions do you remember? What are they? And this is just, there are many more classifications of reactions. What do you remember? There's single replacement, okay, double replacement. What is it? Synthesis. Let's do decomposition, then we'll do combustion. Okay, so that's the way we start out. And there are more, certainly chemists have more classifications than that, but this is what we need to start with right here. But what was interesting is, of these, there are these things called driving forces. Just because you put two chemicals together, why would they react? Why don't they always react? Is that right? We tend to think when you put a metal who likes to lose electrons, if you put it next to a non-metal, usually what happens? What happens is, I want to lose electrons anyway. Yeah, I want to steal them. Well, then they will, won't they? And I'll become an ion, and you'll become an ion, and we won't be able to get away from each other, right? Because of ionic bonding, right? That was a pretty easy one. That would be like metal, non-metal forming compounds, and that might be like synthesis. That could be possible, couldn't it? So the driving force there was the transfer of electrons, wasn't it? Okay. What about this? What do you think the driving force is for combustion? And it's going to be the transfer of electrons. What about this one? Transfer electrons. This one, transfer electrons, but not this one. Matter of fact, we have a name given for reactions who have the tendency, somebody's going to gain electrons and somebody's going to lose. And do you remember this word? We'll revisit this in just a minute. Redox stands for reduction, and what else? And again, even though when I was taught this, my memory trick was Leo the lion says grr. But I will say, for whatever reason, maybe I thought that was just too cutesy, and a lot of your books now say oil rig. Okay, so anyway, whatever your memory trick is, here's what it says. If you were to lose electrons, you would become oxidized. If you gain electrons, you're being reduced, or reduction is taking place. Now I'm going to visit, I'll come back to you in just a minute. All of these are redox reactions, all of them. Somebody's going to gain electrons, somebody's going to lose, you get it? But which ones are not redox? Not redox. That means that the driving force is not somebody gaining electrons and something losing. Can you think of, there are two kinds of double replacement reactions. See if you already know one of them. Actually, you know both of them. I've never classified it this way for you.
Formation of a solid.
Yes, the driving force would be the formation of a solid. That's called a precipitation reaction. I'll show you how to use that chart. We did that before. I'll show you how to use it again. And what is this one? What's the other one that's double replacement and no transfer of electrons? Driving forces. Say it. Yes. Acid-base neutralization. Now, what's the driving force on that one? Yes. Even though a salt is produced, that's not a driving force because that salt might be soluble and there's nothing really driving the reaction that way, okay? All right, so now, formation of water and formation of a solid called a precipitate. All right, so let's start with that one first. We already did the acid base. Got that? So let's do a quick acid base one. Ready? The most famous acid in the world is what? Hydrochloric acid in your stomach. If you go to Home Depot and you want to, hey, you have hydrochloric acid? Oh, no, we don't sell that stuff. You have muriatic acid? Oh, yeah, what's that? Anyway, they call it muriatic acid in the hardware store, okay? You can also go to some dollar stores, and they have this toilet bowl cleaner called The Works. Have everybody seen that? You look on the package. Contains 20% hydrochloric acid. Okay, it's up there. That's a lot of acid. So if you wanted some, you could get muriatic acid, and be really, really careful. Make sure your parents are aware of this and all kind of stuff. But yes, you could actually do a little chemistry with that if you wanted to. Now, so let's do the world's most famous acid with the world's most famous base. And, okay, so we're going to write in some little symbols here, okay? Acids and bases, by their definition, are solutions. Everybody got that? All right, now, they are double replacement, so I should get H2O. Usually it's in the form of a liquid. If it was really, really hot, I guess it could be a gas. And what else? And what we have to do is we have to look this up. Okay, so one of the papers I gave you, let's see if we can find that. My paper. Uh-oh. Did I give you that sheet? Okay, there it is. Oh, there it is. Okay, now, this is what we did this in 10th grade, but let's say you don't remember 10th grade. And what we do is, the only time you would use this solubility chart is a double replacement reaction. That's pretty much when I use it. And what I want to do is I want to know, is this going to be the precipitate? And I'll use it up here, okay? But in an acid base, chances are, most of the time, that the salt's an ionic compound, is going to be soluble. So we'll never see the salt. So if you add acid to water, if you add acid to sodium hydroxide, I don't want you to drink it, but if you did drink it, if you knew they were completely neutralized, it should taste like salt water. Okay? Now, this right here is called the this is called the chemical equation. This is the chemical equation. Now what I want to do is, let's see if we can write the ionic equation. How about the complete ionic equation? Complete ionic equation. Okay? All right, how do you write the complete ionic equation? And this is where I had to fight with you a little bit in the 10th grade because you didn't like this. If this thing here is aqueous, what's actually in that beaker? Everybody should know this. Hydrogen ions, which are aqueous, plus what else? Aqueous plus what else? Aqueous plus, and they do have to have charges on them, aren't they, ions? So you have to have the charges on there. And then what's that yield? Well, in this case, this is my driving force right there, isn't it? And then what happens over here? Well, you said they were aqueous, so. All right, remember that? And the fun part, how do you go from complete ionic to net ionic equation? How do you go from complete to net? This is the fun part. Say it again. Yes, I love that. When I first learned that word, spectator ions, that means whatever you're doing on the left side of the arrow, you're still the same. Oh, we didn't do anything. You just sit around and looked, and like a spectator. And look, see this guy here? You didn't do anything. I had chloride ions bouncing around. At the end, I had chloride ions bouncing around. You're just a spectator. There's no chemistry with you. How about you? No. And so matter of fact, what is the net ionic equation for all your acid-base equations, neutralization equations? There we go. Look at that. That's the chemistry. That's the only chemistry that happens in a acid-base neutralization. You okay with that? That's pretty easy. Now, let's try one a little harder. Yes. And so if you want to do stoichiometry with the net ionic equation, you could. What if I told you I gave you 30 milliliters of 0.5 molar HCl? Okay, so what could you do? What's molarity times volume in liters? What is molarity times volume in liters? Moles of solute. So what is this? What's 0.5 times, 0.03. Anybody give me a hit on that? Is it 0.15? Yeah. Isn't it 0.015? Is that right? Is it 0.015? Yes, no? What is 0.5 times 0.03? Okay, so guess what? Look, if you had 0.015 moles of that, if you had 0.015 moles of this, then how many moles of hydrogen ions would you have? There's only one of those for every one of those, right? Yeah, so if you have 0.015 moles of that, you'd have 0.015 moles of, yes?
Excuse me, Mr. Beatty. May I ask Alex a question real quick?
Yeah, sure.
All right, thank you.
All right, what was it? Okay, so guess what? I can actually jump right to the net ionic equation and do my stoichiometry if I want. What if I want to know how many moles of sodium hydroxide are going to be used? Watch now. 1 to 1, matchy. 0.015 moles of hydroxide ions, but guess what? How many moles of sodium hydroxide would you have then? For every one of these, you get one of those, right? So if you have 0.015 moles of hydroxide ions, you have 0.015 moles of sodium hydroxide. How much water is going to be made? Matchy. You see that? See, there are a lot of people, if you do become a chemistry major, you'll end up probably using net ionic equations on these kind of things. They go a little faster. Okay, what do you think about that? That's kind of the easy, of all the double replacements, that one's not too bad. But let's do the next one, and I need a good example here. So why don't we do a homework problem? here it is. It's number 28. Let's do homework problem number 28. All right, here we go. Write a formula, complete ionic and net ionic equations for the following reactions. All right, let's do the first one. Aqueous sodium sulfide. Let's try it. Let's see how good you are at writing compounds. Aqueous sodium sulfide. Is that it? Is that good there? Now, everybody big chemist says that was true. This is -2. This is +1. Is that right? Okay, aqueous sodium sulfide reacts with aqueous copper 2 nitrate. You say copper 2? Oh, yeah, copper 2. Did you say nitrate? Yeah, nitrate. That's right. Yeah. Okay. Now, this is going to be a double replacement reaction, so go ahead. See if you can finish it and balance it. Finish it and balance it. And I know it's Monday, and you got to just crank it up a little bit. Got to crank it up. You can do that. Double replacement. Okay. Now, is that what you get? No? Okay. How about, do you get sodium nitrate? Oh, 2 of them. Oh, it's not balanced yet. Okay. So we had 2 here and 2. How about that? Do you like that? Okay, now notice we haven't put any symbols here. Matter of fact, I don't think this reaction is going to take place. What's your driving force? Unless you show me there's a driving force, it's probably not going to happen. So we're going to look these up. And I know you can't remember everything, but I remember in 10th grade, I had you tell me the patterns. You know what college professors do? They want you to learn these. Just learn the general rules, and they don't give you a chart. They don't give you a chart like this. They just say, so here's some rules that we should know already. Salts, which are ionic compounds of alkali metals are almost all what? Matter of fact, there might be one lithium compound. So if you're going to have sodium something or potassium something, let's take a look here. All sodium salts, where am I? All sodium salts, they're soluble. I don't have to look you up. If you're sodium nitrate, I know you're, there you go. I'm going to put aqueous after that, aren't I? How about potassium? All potassium salts are soluble. How about another one? How about ammonium? How about ammonium? Look up there. Oh, all those are soluble. Any others? What is it? Hydrogen? Okay. Now, let's look this way. Now look this way. Look for the, not the cation, look for the anion. Almost all of the acetates are soluble, right? What else? Broma. Okay. How about how about chlorides? Not you. Okay, a lot of chlorides are. How about nitrates? Yeah. Oh, yeah. All nitrates are soluble. Anybody else? Chlorates? Let's look at chlorate. Chlorate. Oops, okay, sorry. What's going here? Oh, dang it. By the way, I will give you this chart, okay? Even though in college I'll probably want you to memorize the solubility rules, okay? You can do it. All right, so what about this guy here? I'll tell you right now, if he doesn't form a solid, if he didn't form a solid, we do not have a driving force. We're going to look at copper 2 sulfide. Copper 2 sulfide. Okay, notice that this chart doesn't make a distinction. They act like copper 1 and copper 2 salts act the same. What do you think about sulfide? All right. Now, here's where you have to be careful. On this chart, this particular chart uses S to mean what? Soluble, which means you'll never see me. I'm soluble. But what am I going to put after this? Okay, why am I putting an S after that? Solid. I'm sorry. I'm sorry that happens. S on this chart means you won't see me. S over here means you'll see me. I'm the precipitate, aren't I? Are you with me? So what's the driving force? Kyle, what's the driving force? Why does this reaction take place? Look up here. What is it? Is it double replacement? Is it acid base? Is it the formation of water? Is that what drives it? There's no water here, though. There's no water here. So it's not the formation of water. What is it? And what do you call an insoluble product? What do you call an insoluble product? What's the name of, there's a product. There's a product. What do you call an insoluble product? Precipitate. That's why this is a precipitation reaction. Is it a precipitation reaction? Yes. Is it a double replacement? Yes. Get it? Okay, now, I want you to take the next minute or so. Maybe I cut my finger or something. All right, go ahead, and I want you to do the complete ionic equation, and then do the net ionic equation, all right? Let's try it. What's really in that beaker? And by the way, there's no diatomic sodium. What's in that beaker? Who wants to start me out? Caleb, help me out. What's the first thing I'm going to write down?
Sodium plus.
Am I going to put aqueous after or not?
Yes.
Yeah? Am I going to leave it like that?
Put 2 in front of it.
Yes. I'm not going to put a subscript 2. There's no diatomic sodium. Go ahead. Keep going, Caleb. You're hot.
S minus 2 aqueous
Oh, man.
plus Cu plus 2 aqueous
Whew.
plus 2 NO3.
Not diatomic nitrate? No, there's no diatomic nitrates.
2 NO3 minus 1 aqueous yields 2 Na plus 1 aqueous
Man, I knew you were smart. You're just doing a great job.
plus 2 NO3.
You mean that distributes? Yeah, okay.
2 NO3 minus 1 aqueous plus CuS aqueous.
See you what now?
Not aqueous solid.
You better not break that up. If you break that up, you don't have a driving force, right? You did a great job. You did a great job. All right. Carson, cross out the spectator ions. Is he a spectator ion?
Yes.
By the way, if you see 2 over here, 2 NAs over here, and you don't see 2 over here, you didn't balance it right. Everybody get that? You can sometimes catch your mistakes. Cross out those spectator ions. Go ahead, Carson.
So Na and then nitrate.
Yes? So, all right, so that's called we took the complete ionic equation, turned it into, here's what the net ionic equation looks like. Oops, S minus 2. Sulfide ions bumped into copper 2 ions. And you know what? The force of water trying to keep them apart was not great enough because the force of attraction here was greater, wasn't it? That makes sense to you? Okay. Now, what I'd like to do is pick a harder one. I need a harder one. Okay. Let's try something else. I need a good one.
Sorry.
Okay. I don't have a good one. The second one on that, on number 28 was not that good. Okay. I'll make one up. How's that? Sorry, just wanted to make one up. Bad. Bad. Okay. Okay. All right, now, here's what I do. Even though I might make you, or actually I do, I'm going to make you write out the balanced equation. Then I'm going to make you write out the complete ionic equation. But let's pretend that I really wanted to see the net ionic equation and I wanted to see it quickly. Here's what you should be doing. Everybody here should know this little shortcut. This is a shortcut to net ionic equations. Everybody got it? All right.
What's the first sentence? Is that
Na2.
Okay.
Okay, there you go. Now, let me show you a shortcut. Ready? In your head, it's double replacement, right? What are the two products going to be in your head? Sodium chloride. All sodium salts are soluble. It's not a precipitate. What's the other one? Barium sulfate. Let's take a look. Look up barium sulfate. Barium sulfate. Ah, insoluble. Now, let me show you a shortcut. Ready? This is going to be the solid. Now, you've never done an equation backwards, but I am. I'm going to do it backwards, okay? All right, barium sulfate is like that, right? Okay, the only way you could have made that is to have a barium plus 2 ion and a sulfate minus 2 ion, and I'm done. There's the net ionic equation right there. What if the product was, let's see, what if the product was, okay, hang on, sorry, I'm trying to make these up in my head. All right, just give me 10 seconds here. Okay, what if, I'm sorry. All right, what about that? What if I said aluminum hydroxide reacts with, maybe it reacts with sodium phosphate? Okay, let's do the net ionic equation. What are the two products going to be? Uh-oh. Aluminum phosphate and sodium. I already know sodium hydroxide is going to be what? You cannot be my driving force. So let's look up aluminum phosphate. Aluminum phosphate. What do you think?
It's soluble.
No, aluminum phosphate? I think it says I. Yeah, aluminum phosphate says,
Oh, wait, I was looking.
okay, so let's write that down. Write the compound aluminum phosphate. Oh, bad example. Mr. Fitty. Dumb. Dumb. Okay, we'll do it anyway. The problem is this is +3 and this is -3. Darn it. Okay. Here's what I was trying to get you to do. Sorry. X, Y. There we go. That's what I wanted, okay? So let's pretend like the product that's insoluble is this guy here. Ready? How's the only way you could have made this? How's the only way that could have formed? Two what? Two X's that are -3, two X ions that are -3 aqueous, had to combine with what? 3 Y ions. See that? So that the net ionic equation can get gotten to pretty quickly, can it? Yes.
Which one is plus and which one's
Oh. That's good. That's good. You know what? I should have actually had one of those ready. I thought I could just make one up on the fly. But it's a little bit harder than I thought. Hey, good catch on that one. Tim, good job on that one. You're right. That was plus and that's minus. What do you think? Okay. We only have, there's only really one more thing to do. And that'll be tomorrow, called oxidation numbers. And then I think we should have some time on Wednesday to kind of put this all together. Could you think about the choice, though? I think you need about an hour and a half. So if you feel like on Wednesday, say, I don't want to do 30 minutes in class and I won't listen to the review. Or we could do any combination you want. I guess if you're honest with it, I can do any combination you want. You just why don't you give me an hour and a half somehow.
So if you don't choose to take it on Wednesday, if you take it like at lunch or something, can we use those 30 minutes to like ask you questions?
Which 30?
Like in class?
Yeah, on Wednesday, I think I'd like this review all day Wednesday. We'll be almost done.
Before people take it if they want. Is it like?
What I'll do is I'll be here in the morning. So if people decide to take half it in the morning, I'll just have you over in the corner and we'll talk about whatever you want. Is that what you mean?
Well, like, are you still giving the option for people to take it on Wednesday during class?
If people do that, then we can't really study with them in the room.
I see.
But like, if they take it like the second half of class, then we can ask questions up until that point.
Here's what I need to do. I need to somehow not have Wednesday be one of the options. How about that?
Yeah.
Okay.
Then they could do morning Thursday, lunch Thursday, class Thursday, actual Thursday. I could even do morning Friday.
Okay.
Thank you.
How about that? Is that
That sounds good, yeah.
Thank you.
okay? All right. Let's get rid of the Wednesday option. How about that?
Okay, thank you.
Can I take a picture of the notes? I forgot my glasses at home, so I could